This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. In this section, we're going to examine how operators are specified for user-defined types through a mechanism known as operator overloading. In C++, it's possible to specify the meaning of an operator whose operands are one or more user-defined types through a process known as operator overloading. So in C++, most of the operators in the language can be overloaded. I've listed the different operators here that can be overloaded, which is the vast majority of operators in the language. For example, maybe you have a complex number type. You've created some class which represents a complex number type, and you want to define addition, subtraction, multiplication, division operations for this complex number type. It would be nice if you could just use the operators as you normally would for any other numeric type in the language and just write plus or minus and so on if you want to add and subtract. And you can do this with the language, as we'll see. It's not possible to change the precedence or associativity of operators, so the precedence, the order in which they're applied, and the associativity, whether they're evaluated left to right or right to left, is fixed. You can't change this, but you can attach a particular meaning to the operators, and the way this is achieved is by creating specially named functions, as we'll see. In C++, operator overloading is achieved using specially named functions. So for example, if we have an operator, and this @ symbol here is not an operator in C++, it's just a placeholder for an arbitrary operator like plus or minus or plus plus or minus minus, etc. So if we have some operator that we want to overload, what we do is we create a special function called operator and then whatever the name of the operator is. So if we wanted to overload the addition operator, operator plus, we would create a function called operator plus. And with some exceptions, operators can be overloaded either as a member function of a class or a non-member function. In the case that a member function is used, the first operand of the operator becomes the this variable for the member function. In other words, it's the object that the member function is operating on. And then any subsequent parameters are passed as regular function parameters. On the other hand, if an operator is overloaded as a non-member function, then all of the operands are provided as explicit function parameters to that non-member function. In the case of postfix unary operators, namely increment and decrement operators, there needs to be a way to distinguish between the prefix and postfix versions of increment and decrement, because if you have a variable x, you can say plus plus x, or you can say x plus plus. In other words, the plus plus can either go before or after the variable, and it makes a difference whether it goes before or after because it's a different operator. So because of this, there needs to be a way to distinguish between the postfix and prefix versions of increment and decrement, and the way this is accomplished is providing a dummy parameter of type int to the operator function. So in the case of postfix, increment, and decrement, the operator function has a dummy parameter which has type int that's never used for anything except to just distinguish between the prefix and postfix versions of the operator. And just to give some examples of expressions involving overloaded operators and how they're interpreted, if we have a binary operator, like for example binary addition operator, in which case the operator @ symbol here corresponds to plus. So if we have a plus b, if we overload the operator as a member function, then this would get translated into something that looks like a dot operator plus, and then b would be the parameter to the function, the explicit parameter. So in other words, this variable, star this, becomes a, the first operand of the operator, the one on the left here, and the second operand, b, is passed as an explicit function parameter. On the other hand, if we provide this operator in terms of a non-member function, then both of the operands, a and b, are passed as explicit parameters to the function. Because in the case of a non-member function, there is no this variable, there is no object that you're operating on, therefore all the information has to be passed into the function using explicit function parameters. In the case of a prefix unary operator, for example, like minus, like a negation, in other words, take the negative of a number, for example. So in this case, the @ symbol would be the minus sign. So minus a, if we use a member function, this would get translated into a dot operator minus, and then because there's only one operand, there's no parameters to be passed as explicit parameters to this member function. On the other hand, if we overload it as a non-member function, then the operand is passed as an explicit parameter. And then the last entry I have in this table is for the postfix unary operator case. In other words, for postfix increment and postfix decrement. So for example, if the operator here was plus plus or minus minus, this would correspond to postfix increment and postfix decrement. In these cases, there's an extra dummy parameter that's provided to the function which has type int, and it's never used by anything. It's just there to distinguish between the prefix and postfix version of the operator. So in this case, we have a single operand. In the case of a member function, it's passed using the this variable, in other words, the object that you're operating on, and you have this dummy parameter to indicate it's the postfix type operation. In the case of a non-member function, then both the operand is passed as an explicit parameter, and we still have this dummy parameter, which is just indicating its postfix. As alluded to earlier, not all operators can be overloaded either as a member function or as a non-member function. In particular, some operators only can be overloaded as member functions. And in particular, the assignment, function call, subscript, and member selection operators have to be overloaded as member functions. In other words, they cannot be overloaded using a non-member function. It is possible to provide both member and non-member functions for an operator, at least for the operators that allow both. In this case, argument matching rules are used to determine which of the operator functions will be called. It's probably better to only provide one, because if you provide both, you may get into situations where you have ambiguous function calls. If the first operand of the overloaded operator is not an object of class type, in other words, it's not a struct or a class, then you have to use a non-member function for operator overloading purposes. And I'll go through an example later to illustrate why this is the case. But if you stop to think about it, this is the way that it would have to be. For the most part, the language doesn't really impose any restrictions on you in terms of what the meaning of your user-defined operators are. In other words, there's not really any semantic requirements imposed by the language. For example, if you have some type for which it makes sense to increment the value of an object of that type, there's no requirement that plus plus x, x plus equal to 1, and x equal to x plus 1 be equivalent, where x is some user-defined type that you've created. Of course, it's probably not a good idea to define these things to have different behaviors, because it would be very counterintuitive to people who are using your class. So again, although there's lots of things you can do in C++, just because you can do it doesn't mean it's a good idea. And in this case, it's a bad idea to make these different expressions have different behaviors. On this slide, I have some examples showing how expressions are translated into function calls when operator overloading is involved. So on this slide, x and y are variables of some user-defined type. And for example, if you have the expression y equal to x, if you remember from earlier, the assignment operator can only be overloaded as a member function. So in the case that it's overloaded as a member function, this expression here would get translated into a function call which looks something like this. The first operand of the assignment operator, with the one on the left, will become the variable associated with star this inside the member function. In other words, it's the object that you're operating on inside the member function. And the second operand gets passed as an explicit parameter to the member function. And maybe if we look at another example here, for example, the less than operator, we want to test to see whether x is less than y. In the case of less than, we can overload the less than operator as either a member function or a non-member function. In the case of a member function, this would get translated into a function call that looks something like this. Again, the variable associated with this, in other words, the object that the member function is operating on, is the corresponding to the first operand, the one on the left, x. And the second operand, y, is passed as an explicit parameter to the member function. In the case that we overload using a non-member function, then both of the operands, x and y, are passed as explicit parameters. And by the way, you can actually write code that looks like this. Instead of writing out y equal to x in your code, for example, you could actually write out y dot operator equals open bracket x, closing bracket. But no one wants to write things this way because it's just too verbose. And the whole reason for having operator overloading is so that the code can be less verbose and easier to read. On this slide, we have an operator overloading example using a class called vector. So if we look at this class definition, the class essentially represents a two-dimensional vector, a mathematical two-dimensional vector. It has an x component and a y component that are represented by doubles. And we have a few member functions. We have a default constructor, another constructor that can be used to initialize a vector with a particular x and y component value. And then we have two accessors that allow us to get the value of the x component and get the value of the y component for the vector. Then we have two operators that are defined. Both of these operators are overloaded using non-member functions. Obviously, this is not a member function of any class. And this operator star is not a member function of any class, so these are non-member functions. And we want to, in this case, we want to overload the addition operator, the binary plus operator, in order to be able to add two vectors. So we take two vectors as parameters to this function. For efficiency, we pass them as const references because the vector type is a little bit bigger, so probably it's more efficient to pass by reference. And then we simply return a vector which is equal to the normal mathematical definition of adding vectors. We add them component-wise. So this is the value that's returned. So the returned value is a vector. We also overload the star operator, the binary star operator, in other words, multiplication operator, to perform the vector dot product. So again, what we do is, because this is a non-member function, both of the operands have to be passed as explicit parameters, which are passed as the parameters u and v. So these are the two vectors that we want to take the dot product between. For efficiency, we pass them as const references because the vector type's a little bit bigger. So again, it's probably a little bit more efficient to pass by reference rather than copying the data. And then we just return the value which corresponds to the mathematical definition of the dot product between the vector u and the vector v. And then below I have some code that's using this class. I create a vector variable called u, and I initialize it to have its x and y components to be 1 and 2 respectively. I create a vector called v, and I initialize it from u, so this is going to invoke the copy constructor, which we haven't explicitly provided, but it's provided by the compiler. Then we create a vector called w, and then the interesting part as far as operator overloading goes is the next few lines. So then we say w is equal to u plus v. The order of operands here, or order of operations, is addition first followed by the equal sign, because we have two operators here. We have the operator plus and operator equal, but if you remember operator precedence rules, plus has higher priority than equals, so this will be u plus v first, and then the result of that will be assigned to w. So in other words, this line of code here will get translated into code which looks like this. First, our operator plus function here will get called to add u plus v. The value that's returned is the vector, and then that vector that's returned here gets passed into operator equals to assign it to w. And although we haven't explicitly provided this function, it's implicitly provided by the compiler. Again, remember, under certain circumstances, the compiler will provide a copy constructor for you. On the next line here, we compute the dot product of the vectors u and v, because we say u star v, but we've overloaded star in the case of two vector operands. U and v are both vectors. So this is going to use our overloaded operator star, our multiplication operator, which is defined to perform this operation, a vector dot product. So it's going to compute the vector dot product, return the result. The result is a double because in the case of vector dot product, the answer you get back is not another vector. If you take the dot product of two vectors, you get a scalar. In this case, that's represented by a variable of type double. And then that double is passed back and assigned to c. So this u star v is going to be translated into a function called that looks like operator star, and then passing u and v as parameters. Since c is a built-in type, c is a double variable, there's no assignment operator function call that's required to assign the return value from u star v to c. I mean, there's some code that's required to do this, but it's not using an operator, any operator overloading, because it's a built-in operator for one of the built-in types in the language. On this slide, I have another operator overloading example. This one is for a class called array10. And essentially what this class does is it represents a fixed size array. A fixed size array of doubles where the array has 10 elements in it. So it's basically a fixed size 10 element array of doubles. And we have three member functions that are provided here. We have a default constructor for the class, which simply sets all the elements of the array to be 0. And we have two operator functions that basically overload the subscripting operator for the class. the basic idea is we want to apply or provide a subscripting operator so that the user of the class can access individual elements in the array that's represented by the class object. So if we look at the subscripting operator functions, there's actually two of them. The only difference between them, or the main difference between them, is one is a const member function because of the const keyword here. This one doesn't have any const keyword here, so this is a non-const member function. So we basically have two different versions of the subscripting operator. One is a const member function, one is not a const member function. Both of them basically have a similar sort of behavior. The subscripting operator takes a single parameter, which is whatever type you're using to index into the element that you're subscripting. In our case, we're using integer indexes, so we have an int type parameter that's passed. And all we're doing here is we're just returning the indexed element of this array data. So the user passes in a particular index, and then we return a reference, because of the reference symbol here, we return a reference to this element. In the case of this function, we return a const reference, because of the const keyword, a const reference to double. In the case of the second function here, we return a non-const reference to double. But otherwise, these two functions look very similar. So if I go down and look at this code below, called this function func, that's using the class, I can make some additional comments on overloading. So inside this function, we create an array10 object called v, and then we want to index into this array v and change the second element in the array. Remember, the elements number from 0, so 1 is actually the second element in the array. And we want to set that second element equal to 3.5. So how does this work? Well, when the compiler sees we're applying the subscripting operator, in other words, the square bracket operator, to this user-defined type v, it goes looking for an operator square bracket function defined for this particular type, and it notices that there's two of them. It's overloaded twice. One is a const member function, one is a non-const member function. It has to decide which of these two functions to call. And basically what it will do is it will call the one that's a better match for the particular object that we're invoking the subscripting operator for. In this particular case, we're invoking the subscripting operator for the object v. And when we define v, v is not a const object. It's non-const. In other words, we're allowed to change v. So because of this, when the compiler gets to choose between a const member function and a non-const member function for operator square brackets, the one that's the better match is the non-const member function, because the object v that we're dealing with here is not const. So because of the way that the rules of the language work, the non-const member function is deemed to be a better match. So the subscripting operator that gets invoked here is going to be specifically this second function here, the one that's a non-const member function. Because of this, this means that the return value from this function is a non-const reference. In other words, it's a reference to something that we're allowed to change. And this is really important because of the way that we're trying to use the subscripting operator here. What we're trying to do is we're trying to take the reference that's returned by the subscripting operator, which is essentially the expression on the left-hand side of the equal sign, and then we want to assign 3.5 to that thing on the left-hand side of the equal sign. So it's critical that the thing on the left-hand side be something that's not const, because we can't assign 3.5 to something that's const, because we can't change the value of something that's const. But because the particular version of operator square bracket that's being invoked here is this function here, in other words, the non-const member function, and it's chosen to return a reference to something that's not const, because of this, we're allowed to change the thing on the left-hand side. In other words, this left-hand side is going to be a non-const reference to double, in other words, a nickname for a double that we're allowed to change, and then we're going to assign 3.5 to that nickname. So this is a perfectly legitimate and valid thing to do, and we don't have any problems. This will compile fine, this line of code. Then we go on to the next line here, and we index into our array v, and accessing the 1th element, which is the second element in the array, and then we assign its value to c. And there's not really too much interesting going on here. This is going to invoke, again, the non-const member function version of operator square brackets, because again, v in this case is a non-const variable. Therefore, when the compiler is forced to choose between the const member function and a non-const member function version of operator square brackets, the one that's the better match is the non-const member function. So it calls this function, it will return a non-const reference to double, Then we read the value of that double and assign it to C. Then if we proceed on to the next line here, now we're creating a const array 10 because of the keyword const. So U is an object that cannot be changed once it's been constructed. Then we proceed on to try to index into this array and then assign 2.5 to that particular element in the array. Now this line of code is not going to compile. This is an error, and it's really, really important to understand why it's an error and what's actually wrong here. Because if you don't understand this, you're going to have problems with writing const correct code. In other words, code that correctly makes use of the const qualifier. In this particular case, U is a const object, right? Because when we define the variable U, we set its const, meaning that it can't be changed. So when the compiler tries to apply the subscripting operator here to U, it's going to go looking for a subscripting operator that can be applied to an object of array 10, and it notices there's two different versions it could invoke, this function here or this function here. So it then needs to decide between them. And the only difference between these functions is this one is a const member function and this one's not. So when it's choosing between them, because this object here, U, is const, the member function that's a better match is the one that is a const member function, because it's making the promise that it won't change the object that's being operated on. And in this case, we don't want the object being changed because U is const. So this we'll call the first function, and this is where the problem arises, because this first function here returns a const reference to double. In other words, it returns a reference to a double that cannot be modified. So after the subscripting operation returns, the subscripting operator function returns, effectively the left-hand side is replaced by a const reference to double. In other words, it's a nickname or alias for a double that can't be changed. And the thing is, we're trying to assign 2.5 to this variable that can't be changed. This is a problem. This is a compile error, and the code will fail to compile. If we continue on in the example to the last line here, this line of code will compile fine with no problems. Again, we're trying to apply the subscripting operator to the object U, which is a const object. So this is going to invoke the first of the two functions, the first of these two operator square bracket functions, which will return a const reference to double. So effectively, the right-hand side of the equal sign gets replaced by a nickname or alias for a double that's const. But this doesn't cause any problems because we're not trying to change this const quantity. We're just going to read its value and assign it to D. So this poses no problems. As discussed earlier, in C++, many of the operators that can be overloaded either as a member function or as a non-member function. Therefore, the question will naturally arise when you're trying to overload a particular operator, should you use a member function or a non-member function to achieve this? And really, there's two main considerations when making such a decision. One is whether or not the operator, in order to do its job, would need access to private members of the class. If it does, then it would be very natural to use a member function to implement the operator, because if you use a member function, because a member function by definition belongs to the class, it has access to all of the private members of the class. On the other hand, if you implement an operator using a non-member function, because the non-member function is not a member of the class, it's not part of the class, it can't access any of the private members of the class. Another consideration is whether the first operand of the operator is of class type or not. If the first operand is not of class type, in other words, it's some built-in type like float or double or int, then you cannot overload the operator as a member function. The reason why is that if you're talking about a built-in type, there is no member functions for a built-in type. Int, for example, has no member functions because it's not a class. Therefore, you can't put a member function into the int class because there is no int class to begin with. Int is not a class, it's a built-in type. So these are the two main considerations, I would say, when trying to choose between a member versus a non-member function. On this slide, I have a code example to further illustrate the issue involved with whether the first operand of an operator is of class type or not, because this will have an impact on whether you choose to overload the operator using a member function or non-member function. So in the particular code example we have here, we have a class called complex, which represents a complex number. There's two data members, x underscore and y underscore, which correspond to the real and imaginary part of the complex number, respectively. We have a few member functions. We have a constructor, which takes two double parameters, which correspond to the real and imaginary part for the complex number that we're creating. We have a member function called real, which returns the real part of a complex number. A member function called imag, which returns the imaginary part of the complex number. And then down below, we've overloaded some operators using non-member functions. The first one here, we're overloading operator plus, in other words, the binary plus operation, to add a complex number and a double. We've also overloaded it to add a double to a complex number. And these are two distinct operations. The order of the operands matters. So if we want to provide both of these pieces of functionality, we need to overload operator plus twice and provide two functions. The first of these functions could have been implemented as a member function. Here we've implemented as a non-member function, so both of the operands of the addition operation are provided. The complex number parameter A corresponds to the left operand of plus, and then the double parameter B corresponds to the right operand of plus. If we instead implement this as a member function, what happens is the first parameter becomes associated with the this variable, in other words, the object on which we're operating upon. And then we only have one explicit parameter, which is the second operand of the addition operation, which is this parameter here. And both of these would be, possible to do, and perfectly valid choices. Probably the non-member function would be a better choice, at least in my opinion anyway. In the case of the second operator plus function that we have here, this one has to be implemented as a non-member function. And the reason for this is that the first operand of operator plus does not have class type. It's not a class or a struct. It's a built-in type. And because of this, there's no way to make this into a member function implementation, because if we wanted to make this operator plus into a member function, it would have to become a member of this class. In other words, double. But double is not a class, it's a built-in type. So there's no class in which we could put the member function for operator plus into, because double does not have class type. It's not a class type, it's built in. So for this reason, we have no choice. We have to implement this with a non-member function. And then down below, I have a code snippet that uses the class, this function myfunc, to further illustrate the point. So here we create a few complex numbers, one called A, one called B. We create a double called R, which is initialized to 2. And then we perform two addition operations, which are involving complex numbers and real values, the double value in particular, R. This particular operation here will get translated into either this particular expression here, operator plus AR, in the case that we use a non-member function to overload the operator, or it would get translated into A dot operator plus R in the case that we use a member function. And both of these are perfectly reasonable, and which one would get chosen would depend on which of these options we chose for implementing this operator. But in the second case here, where we're adding the double of the two parameters to or operands to the addition operation, the first one is a double in this case. This one here would have to be implemented using a non-member function. In other words, it would have to be translated into something that looks like this, because the first operand is of built-in type. It's not of class type. And because of this, we couldn't use something like a syntax like this, because R would have to correspond to the class that we put the member function for operator plus into, but because R is double, we would have to put a member function into the double class. But of course, double is not a class, it's a built-in type, so there's nowhere to put the member function. So we have no choice in this case. We have to use a non-member function to implement operator plus. As mentioned earlier, the assignment operator is one of the operators in the language that must always be overloaded as a member function. Consequently, an assignment operator is always a member function of a class. Now, although a class can provide many different overloads for the assignment operator, one particularly important assignment operator is the so-called copy assignment operator. So if we have a class called capital T, the member function operator equals belonging to that class that has exactly one parameter that's an L value reference to T is known as a copy assignment operator. And the purpose served by a copy assignment operator is analogous to a copy constructor. A copy constructor, if you recall, is something that's used to create a new object of a class by copying from an already existing object. What a copy assignment operator does is a similar thing. The only difference is that the thing that you're copying into is an already existing object. So in other words, it copies or propagates the value from an already existing object to another already existing object by using a copy operation. Now, if no copy assignment operator is specified and some other conditions are satisfied, namely that there's no move constructor or move assignment operator specified, and we'll talk about move assignment operators shortly, a copy assignment operator is automatically provided by the compiler. And what this automatically provided copy assignment operator does is it copy assigns each data member. So it uses each data member's copy assignment operator to copy it, or for built-in types, it uses a bitwise copy. Now the copy assignment operator for the class T typically has a signature which looks something like this. The critical thing is it takes an L value reference to T. If it didn't do this, it wouldn't be a copy assignment operator. Normally a copy assignment operator will use a constant reference, because the copy assignment operator, by definition of what a copy is, it doesn't change the thing that's being copied from. And this particular parameter here refers to the thing on the right-hand side of the equal sign. So it's the thing that you're copying from, which shouldn't be changed by copying. Therefore, the reference should be a const reference. And although it might be a little bit counterintuitive, it does actually return a value. It's not void, the return type. And the reason for this is to allow some kind of constructs like what's shown below. For example, if we have three variables of type T called x, y, and z, we can do things like chain together equals like this, and this will do what you would expect, which is probably what you would expect x equal to y equal to z to do, is that after this line executes, both x and y will be equal to z. And in fact, this is what it will do. And the reason why this works is because we're returning an L value reference type for the return value, an L value reference to T. And in particular, the return value is just returning a reference to this. And this allows these assignments to be chained, for example, and allows other similar sorts of constructs. One thing I need to point out is that you have to be careful for the case of self-assignment. When you're doing assignment in your code, there's the possibility you might end up with a line of code that looks like x equal to x. And for some types, this needs to be handled differently. It depends on the particular class that you're implementing, but for some data types, self-assignment needs to be treated in a fundamentally different way from the case of non-self-assignment. So as I mentioned, when implementing copy assignment operators, often the case of self-assignment needs to be treated in a different way from the more common case of non-self-assignment. And in particular, when the data structure involves references or pointers, this is often the case. Now, you might say, wait a minute, I mean, is real code ever going to have self-assignment? Because who's going to write a line of code that looks like x equals x? This would be kind of ridiculous, right? But in fact, self-assignment does happen relatively frequently, but it happens in a more indirect sort of way. And in practice, the typical way in which this sort of thing happens is something like the scenario that I have illustrated on this slide in this code example. So for example, you might have a function, for example, called do something, and it takes two parameters, x and y, of the same type, some class user-defined type, some class type called someType, and then inside this function body, somewhere it has a line that looks like x equal y. Well, when you're writing the function do something, x equal y does not look like self-assignment, but the thing is it could become self-assignment, because notice that x and y are passed by reference here. So x and y are both nicknames or aliases for already existing variables. And the issue is that the person who uses this function, the user of this function, do something, might write code that looks like this, like what's shown in this function myfunc. So we create some variable called z that has the type someType, and then we call the function do something above, passing z as both parameters. When we do this, do something will basically do self-assignment, right? Because when we pass z as both of these parameters, it means that this first reference parameter is going to refer to z, and the second reference parameter also refers to z. So x and y are both aliases for z, and then when we say x equal to y, really what we're saying is z equal to z, and this becomes self-assignment. So this is the kind of more subtle way in which typically self-assignment will manifest itself in practice. So it does occur in practice, so you have to make sure that you handle it correctly. But it usually doesn't happen in as direct a manner as someone literally writes a line of code that looks like x equals x. Another very important type of assignment operator for a class is what's known as a move assignment operator. So for a class T, an assignment operator that has exactly one parameter that's an R value reference to T is what's known as a move assignment operator. So a move assignment operator is analogous to a move constructor. So if you remember from earlier, a move constructor is a constructor that's used to create a new object from an already existing object by moving. In a similar way, a move assignment operator is used to assign, in this case to an already existing object, the value of another object by moving. So basically it's propagating the value from one existing object to another existing object by using a move operation. Now, if no move assignment operator is specified and certain other conditions are satisfied, namely that there's no constructor, copy move constructor, or copy assignment operator specified, then the compiler will automatically provide a move assignment operator for you. And what this automatically provided move assignment operator will do is it will move assign each data member by using a move assignment operator for class objects and using bitwise copy for built-in types like int and float and double and so on. A move assignment operator for the class T typically has a signature which looks something like this. The critical thing is that the parameter to this operator has to be an R value reference to T. This is what makes it a move assignment operator as opposed to some other type of assignment operator. And for similar reasons as the copy assignment operator, this operator returns an L value reference to T, and the reference is a reference to star this. This is what's returned. And then lastly, one comment with regard to self-assignment. Unlike the case of copy assignment, when you're doing move assignment, self-assignment should probably never occur in any sort of sane code. You might want to, when you're writing a move assignment operator, put an assertion or some check in your code just to make sure that someone's not trying to do something insane and call your move assignment operator doing self-assignment. But because of the way move operations are used in the language, self-assignment should never occur in any sort of reasonable circumstances. On this slide, I have a copy and move assignment operator example. So the class that we're given is a class called complex, which is just an implementation of a complex number type. We have two data members for this class, the x underscore, which corresponds to the real part of the complex number, and y underscore, which corresponds to the imaginary part. We have a number of different member functions. The first few are constructors. This function here is a constructor. It takes two parameters, x and y, but because they have defaults, it can also be called with no parameters, because both of these parameters have defaults, meaning that this is actually a default constructor, because a default constructor is any constructor that can be called with no parameters. And because both of these parameters have defaults, we can invoke this with no parameters. Then we have a copy constructor and move constructor. This is a copy constructor because it takes an L value reference to complex, and this is a move constructor because it takes an R value reference to complex. Then we have a copy assignment operator. This operator is a copy assignment operator because of the fact that this is parameter type here is an L value reference to complex as opposed to an R value reference. And if we look at what the copy assignment operation does, it checks to see whether this is equal to the address of A. And what this is doing is it's checking to see whether the object on the left-hand side of the equal sign is the same as the object on the right-hand side. Because if this is true, then this would be equal to the address of A. If these two things are equal, this means that you're doing self-assignment. You're having a line of code that looks something like z equals z. And if in the self-assignment case, you don't need to do anything. It's only in the case that these things are not equal, in other words, in the case that you don't have self-assignment, that you actually need to do some work. And the work you need to do is just assign the x component from the complex number A to the x component of the variable associated with this, in other words, the object that you're operating on in the member function, and assign the y data member from A to the y data member of the object that you're operating on. And then because it's an assignment operator, you return a reference to star this. And we're returning a reference here. Then if we move on to the assignment operator, in this case it's a move assignment operator because we have an R value reference to complex as the parameter type here. Again, with move assignment, we don't need to check for self-assignment. So we basically just assign the x and y components of the complex number, in other words, the real and imaginary parts, and then we return a reference to star this. And then I have some code down below here which illustrates the use of this class. So we create a complex number called z with the real part 1 and the imaginary part 2, and another complex variable called v with the real part 1.5 and the imaginary part 2.5. And then we have two lines below which are doing assignments involving these complex variables v and z. The first line here, we have v equal to z, so this is going to get translated by the compiler into a function call that looks like what's shown here. In other words, it will get changed into a function call which invokes the member function operator equals, and it passes as a parameter z, the second operand of the equals or assignment operator. This next line here, v equal complex 0.0, 1.0, on the right-hand side of the equal sign, essentially what we're doing is we're creating a temporary variable, which is a complex number that holds a complex number with the real part 0 and the imaginary part 1. And then this particular temporary variable is going to get passed into the operator equals function. So this temporary variable here gets passed into this function, and then it does its thing. There's one subtlety here which I'm not going to deal with on this slide because it requires a little bit more in-depth knowledge of C++ beyond what we have. What I'm not going to do is I'm not going to attempt to explain how it is that the compiler decides whether to call the copy assignment operator or move assignment operator in each case. In other words, if you're kind of thinking more carefully about some of the things on this slide, you might be wondering, this call to operator equals here and this call to operator here, operator equals here, which function actually gets called in each of these two cases here? Because there's two operator equal functions. There's this one, the copy assignment operator, and then there's this one, the move assignment operator. And the subtlety is, how does the compiler know which one to use? At this point in your learning C++, it's sufficient to know that as long as you write your code appropriately, in other words, you make your copy assignment operator correctly do a copy, and you write your move assignment operator to correctly do a move, the compiler will always call the appropriate one. As for how it makes this decision, we'll defer discussing this until much later, because it involves more complicated issues with the language.